So in this video, we're going to continue our process for describing the electric field at an arbitrary point around a uniformly charged object. So for now, these differential equations that we just derived prior for our simple example for a one-dimensionally charged object, like a wire, we're going to set this aside for now. We're going to look at something called an intensive property. So our next step is to find an intensive property. So what is an intensive property? An intensive property is some property that is uniformly constant throughout your entire system, or in this case you could say object. It doesn't matter what part of the object you look at, or even if you're looking at the entire object, this property is constant. So let's look at our wire for the time being. So let's reconsider this wire that we were starting with in our example. We decided to say, well, we're going to consider only this part of the wire along the entire wire of length L. And now if we just consider that small charge, it also means we're only considering a small part of the length of this wire, dl. Now the charge per unit length of this wire is the same throughout the entire wire. It doesn't matter if we're looking at this part of the charge, this part of the wire, or if we're looking at this part of the wire, or this part of the wire, or any arbitrary part of the wire. We just know that the charge per unit length is the same throughout the entire wire. So we can call this a variable called lambda. Lambda is an infinitesimal charge divided by an infinitesimal length. But isn't it also true that the total charge of this wire, which we can call Q, is also this divided by its total length is also a constant, and it's equal to that very same constant, which we will know as lambda. So this is our charge per unit length. And this is what we use to describe this one-dimensional wire. Okay, so let's try to make some broader generalizations here about this intensive property. So here we're going to write intensive properties for uniformly charged objects. Okay, so we'll try to make this generalization by first looking at dimensions in which our objects exist. Give a quick simple example. Describe it by some symbol. And look at what its units are. So let's go ahead and start filling this table in. So what if we have a zero-dimensional object? Well, that's the same as a point charge. So it can be described only by one constant, what its charge is, assuming that charge does not change. And we can describe this with the units of Coulomb. Next, we consider a one-dimensional object, which is basically what we have in this example here. and we can describe that as a wire of length L. Okay, so we can describe this by lambda, as we had before, which is basically its charge per unit length. Okay, so nothing new there, and its units are coulombs per, let's say, meters, right? And now we're going to look at a dimension we haven't considered yet, a two-dimensional object. We could consider this as a plate. So a plate can have a bunch of charges on it as well, and those charges distribute themselves across an area of A. So we can call this the symbol sigma, which is our charge per unit area, should those charges distribute themselves uniformly across the plate. So I can write this as coulombs per meter squared. If I'm sticking with meters, I could also write this as centimeter squared or decimeter squared. Doesn't matter, it is per unit area. Similarly for the wire example, and you'll see so for a three-dimensional object as well. So what about our last dimension that we can easily visualize? We can consider here a sphere. So that sphere can be characterized by some radius r, or more generally for 3D objects, we can say volume. So we can call this by Greek symbol rho, and we'll say this is our charge per unit volume. So, whoops, running out of battery. But now here we can call this as coulombs per meters cubed if we're sticking with that convention. So these are all examples of intensive properties, and the one that we have in our example is a one-dimensional wire. So we'll continue more on how to deal with this step, or actually how we use this step for our next step in another video.